Well, well, long time no see, everybody. I hope you are well. It is, at the moment, I believe, about 1:30 in the morning, Australia time. And you know what? It's all good. I have been sitting here just playing with particles. Playing with particles. That is not a bad joke. Not a dirty joke, actually. And I have just been playing around with all versions of the equations and just having fun backwards and forwards. That's what I like to do. And using all of the sub-equations to create the 3D quantum wave particle. And that is a snapshot in time, because the actual particle, National 90, one of my best friends, is actually a four-dimensional wave. So a snapshot in time makes it 3D. That is the interesting thing about it. So it is great to see everyone. Anywho, so I want to go to sleep, but I thought in the meantime I will just give you the basics first on how to construct this wave. So the wave, my lens, my friends. Hello, good to see all of you guys. So I'm going to try drawing on this whiteboard. Everyone's asleep, so I'm down here in the study to try and keep things peaceful. But what I want to do is show you the 3D wave function, which we can draw. You can draw it in different ways. You can do X, Y, and Z. But this way we're going to use the radius and the double angle. So you know what I'm talking about, love, when I draw like a sphere. This is supposed to be a sphere, right? And how do you draw a sphere? I don't know. Maybe if I go like that, does that look like a sphere? I don't even know, right? But that is made up of two angles, right? You've got the angle this way, okay? And then you've got the 3D angle this way. Because, hey, Malitza Sada, long time. Lovely to see you all. I am great, my dear. Look at the back of my neck. I'm just gone dark as anything at the back. There you go. All right, so we have here the two angles. We got theta and we've got phi. These two angles, you got, like, for example, with the globe, that's all you need to make a globe. You just have the equator. Oh, I miss you too, my dear. It's lovely to see you guys. I think this is the longest I've been away from Periscope for like a very long time. But that interview yesterday took it out of me. I don't know why. I think being around humans and doing all those calculations, which is so funny, I actually relax by doing my physics. Like the exact opposite of all the rest of humanity. Anyway, right? So that makes the globe, right? You've got the equator type of thing. Sorry, you got the longitude and the latitude, and you combine them, you get a globe. But then the size of the globe is from the radius on the inside, right? So it's all the energy you were around. I think so. It was a bit too much. It's a bit too much. All right. And so to make the whole equation, we've got this section, right, which is y. And if you guys remember, we've already done this. Y, M, and L. Okay. And M and L this is the angular function of the wave function, right? And we have M, which from memory is the magnetic number, banter is fun, and L, which is the azimuthal number, which is actually describes the orbital, the type of orbital of the electron around the nucleus. And that part I was sitting on today, it's not part of the course, but I was just looking at it for fun about the mathematical descriptions that were created in the early 1900s by freak geniuses. And I've been just sitting around, mucking around with it. So, like, for example, here you have like the nucleus, and then you have an electron. And instead of going around the nucleus, what goes on, it's not actually moving. We think it's moving, but what's going on is that it can actually go like this. It can go like that, and then like a butterfly. Like it can sort of go around like that, which is really crazy, because then you can have another one in 3 dimensions sort of going this way. And then it looks like a rose petal. Isn't that really bizarre? So I was looking at the maths behind this, but basically if you were to look for an electron around this nucleus, depending on the type of nucleus, you would have a more than 90% chance of finding it at certain parts here, but outside you would like almost never find it at all. But it's sort of like a wave, and it's blurry if you zoom in. It's a very bizarre concept. It's a standing wave, and you sort of find the particle somewhere in there. Very crazy. The other side of this is the radial equation. So the radial equation is actually shaped like this. R, and from memory, if I can remember this, it goes like this. N and L. N is the ooh, I forget the name. I think it's called the prime quantum number. So it's the ultimate gangster quantum number, and that talks about the energy state of the system. Right, so let's just use a regular one. I'm gonna do hydrogen later in another episode, but because it's like 1:30 in the morning, I'm gonna relax. But if you have, right, let's say you have an electron going around here, right? This is the lowest energy state. So when it's relaxed, you know, it's just hanging out, right? It's going to be this distance away. So this distance, that'll be n equals 1, right? But when you pump in some energy, right, into the thing, it can actually go out, right? And it goes out to the next level. So that could be n equals 2. And then n equals 3 is further, and they go further and further out, right? We spoke about this before when I talked about the elevator, right? So that there is that number, right? L, so where am I? L is the shape of this, what do you call it? The shape of the orbit. I don't care what you teach us. I only wanted to see you forgive my ignorance. Hey, my friend, that's a very kind thing to say, and it is lovely to see you. Trader, Melissa, and Kano. My friend, it is a pleasure. Always a pleasure to talk to you and to know you're okay. It makes me feel very good. It really does. Same with all of you, Melissa and Banta, who's temporarily disappeared, and G Kano, all you guys. I love it. All right. So basically, I wish I could do a better job. I want to get computer animations. Actually, I'll see if I can find a globe. Maybe I've got a globe somewhere. Oh, actually, I do have a globe. Oh, look at this. Do I have a globe? Yes, I do have a globe. I'm looking around in this study for a globe. Oh, there you go. Here's a globe. Right? So, right, the shape of the globe, okay, that's the orbit. So, have a look at this. I'm hoping this will sink in one day. Given enough time, absolutely. So here is a globe, right? Now, the distance from the center to the outside, right, is the radius. So the bigger the radius, the bigger the globe will be, right? Now, that's the radius equation, okay? Then you've got the shape of the globe. Now, the shape of the globe is made by, right? It's made by the circle this way and the circle this way. So if you look at this one, right? Have a look at that. It's more like an egg, right? Now, the reason this is more like an, I don't know if you can see that, but it's sort of like an egg. Let me turn the camera. Whoa, almost fell over. All right. So have a look at that, right? It's more like an egg. Now, why is that the case? Because the circle this way is actually an ellipse, but the circle this way is a circle, right? So that means that it's going to become more like an egg shape, because the circle that makes this dimension, right, is longer than the circle this way. So it makes an egg shape, right? Now, if it was the other way, if this circle was more of an egg shape and this was a circle shape, then it would look like this. So I hope that sort of explains how mathematically you can build a sphere, right? So basically, you've got the circle this way, you've got the circle this way, right? And then you've got the radius, which shows the size, and that's how you create a sphere mathematically. So that's what we're doing here. This is the radius from the inside all the way to the outside, and then this are the two circles. It's the angular wave function. So it's one angle that goes this way and one that goes that way, and that creates your sphere mathematically. That's how it's done. So that's what I wanted to talk to you guys about. Now, the actual mathematics behind it, where am I? The mathematics behind it, I'm not going to do today. Today was the concept. And I just spent a few hours just writing them over and over, like, and looking at them in different ways and how they mix with reality. And here are the equations. Pisses me off is the great force. The great force. You've lost me on the great force. More maths. Yay! More maths. Anyway, so the neutrons are held by a great force. Are you talking about the strong force? I think you mean the strong force. I believe that's what you're referring to. Yeah, the strong and weak force. Yeah, I was wondering. I like the great force. It sounds better. The great force is like, we must summon the great force. Yes, Captain. That is too good. Anyway, so yeah, I lost where I was going with this. Anyway, I'm going to show you later how to construct all of these, but it shows the limits. Yes, this is true. This is true. Definitely shows limits. Now, what am I doing? I'm trying to dry this board of knowledge. This is correct. Limits of knowledge. Well, you know, there's a lot of interesting stuff that we can talk about with the quantum particles, because they're not actually particles, they're waves and particles at the same time. It's a very, very weird concept. Like sometimes I think about it, right? And then sometimes it'll come to me, I'll actually see it. I'll see the fact that it's a wave and a particle. And then there are times when it just disappears again. But I imagine it's like a guitar. When you strum the string, as it's being strummed, you hear the sound, and that sound is like a particle. So in our universe, the particle is sort of like, you know, when you get a wave and you mix it with the quantum field that we can't see, it creates like a sound, and that sound is the particle that we're made up of. So we're all just like frequencies type of thing. It's very, very interesting concept. All right, so what we're going to do next time is we're going to put those two things together. So we're going to combine theory of relativity, understand it, close, and close the book, and it disintegrates. That's awesome. That's so true. All right, so if you look at this, right, this is what we just did. So we did, this is the radius function, which is the energy level and the momentum, right? And then we've got the angular function, which has the magnetic number and the azimuthal or angular momentum number. Okay, when you combine them together, when they combine their forces, you get this. You get the three-dimensional wave function, right? N, L, M. And that is the 3D wave function. You're too dumb for this. No, don't be silly. You just haven't been taught it. That's all. It's not that hard. All right, so I'm going to show you what it looks like. All right, that's all we're doing today. I'm not going to show you the rest of the actual mathematics. I'm going to show you what that looks like. All right, I just want to know why coins aren't magnetic. They're not magnetic because the atoms inside the coins are not aligned. If they were aligned, then you would get the magnetic. You can actually magnetize a coin, by the way. You can magnetize it by, and I'm not saying to do this, right? I think this is illegal, but if you heat up the magnet, if you heat up the coin, he's a cheap bastard. This is awesome. This is the best lecture. If you heat up the coin and then you let it cool next to a magnet, then it will magnetize. All right, so because all of the particles are all like, but when you align them properly, so they're all standing all in the same line, then all of their individual magnetic fields all align, and you get one big magnetic field. A magnet to my car bumper. Yeah, you could. All right, so let us show you what the wave looked like and collect change. That is too funny. Here are some of these 3D spheres, right? And they don't look exactly like spheres, as you can tell. Have a look at this. If the camera wants to flip, I'm not sure. There we go. There we go. I've showed people this before, right? But we're talking about them from different ways to describe them. So you can see that's a sphere. Some of them look like donuts. Some look like this. This is actually the same four-dimensional object, but it's four-dimensional, and we've taken 3D snapshots. But this is all one object in 4D. So it's very hard to see. But basically, this universe, you've got to imagine it's sort of like a book, right? Actually, talking about books, the hardcover has come in. Here it is. Make sure you go to Ex Libris and get it, Speaking Human. You can download the audiobook actually from exlibris.com. And I'm going to soon sell signed copies on, I think it's called Booktopia. I'm going to sell signed copies on Booktopia as well, which is going to be pretty cool. So that's The Tragedy of the Retarded Genius. All right, make sure you get that. So anyway, the point is you got to imagine this book as four-dimensional. Okay, let me put this here so I can talk to you guys. All right, so imagine this book as four-dimensional, right? So imagine that this is, so here is the past, and let's say that the present is this page, and the future is over there, right? So it all exists in 4 dimensions, but we're traveling, as you're reading the book, you're traveling through time. So that's what's going on now. In terms of the relativity thing, you know, you might be reading the book faster than someone else. So you're going to get to the future, which is the end of the book, before someone else. That's basically relativity. And all of that is only possible because the past, present, and future already all exist. So there you go. That's a little thing I wanted to share with you guys. I hope that helps conceptually. And that's all I'm going to talk about in today's lecture. I really wanted to show you the mathematics, but that'll be next lecture, and you'll need to know like the calculus if you want to get into that. So this is next lecture. We're going to go through all of these. You know, we're going to use every single equation to end up constructing this whole thing here. The whole sphere is going to be made up of all of these, right? And basically it's these. Now what's interesting is that mathematics is actually the simple maths. The past, present, and future already exist. Yes, they all exist, but we experience it in mathematics. Not just mathematics, in the universe as well. The universe is four-dimensional. It's a four-dimensional object, but we only see it as 3D. We experience it as 3D, but actually, we do experience it in 4D because our future self is experiencing the future. Our past self experiences the past, right? So all of those are experiencing them all at the same time. But we only inhabit one slice of our four-dimensional being. Paint something! Yay! All right, so lovely to see everybody. And that's about it for this lecture. It's probably almost 2 in the morning, so I'm going to go to sleep. And I will be doing more mathematics and heavy-duty stuff on Gabversity at another date. There's a lot of stuff I want to talk about. I really want to talk about DACA. I wanted to talk about what do you call it? The illusion of the fight on both sides of climate change. I wanted to talk about the sexuality of men. There's so many things, but I just have no time. And today I was so down after the interview. So I will love you all and let you go. And don't forget, I'm going to keep plugging this bad boy. Oh, by the way, the massive book launch is coming soon. It's coming soon, my friends, probably in under 2 months. The massive book launch is coming. And everyone who pre-ordered will get their copies before that, I'm pretty sure. And there it is, exlibris.com. Make sure you go. My plan is to get at least 50,000 copies out in the next year. That's my plan. Because we need to share with the world the life of the retarded genius. Love you all. Gabversity, where facts don't care about your feelings. Yes, you in particular.